You can multiply vectors by some scalar, and you'll get a scalar multiple, like I mentioned in a previous video. And when you have a scalar multiple that is larger than 1, you're stretching your vector. If you have a scalar multiple between 0 and 1, you're shrinking your vector. And if you have the negative, if you're multiplying by a negative, then you're changing the direction of your vector. In words, let k be scalar, then kv is a scalar multiple of the vector v. If k is greater than 1, then the vector is stretched. If k is between 0 and 1, then the vector is shrunk. And if k is negative, then the vector direction is opposite. So I've drawn 4 vectors here. Vector v is our original blue vector. Twice v is shown with the green vector. Half of v is shown with the yellow vector. And negative v is shown with the pink vector. When k is equal to 0, this is what we call the 0 vector, and it's denoted by 0, and it has a magnitude of 0 and no direction because it's not there. We're going to talk about component form of a vector now. When we have a vector that is sketched with its initial point on the origin, we call that standard position. So if you're looking at an xy plane and you have your initial beginning point of the vector starting at the 0, 0 point, then that is in standard position. We're going to name a couple of points, and they're going to be points in the plane, and then we're going to call our vector the distance between those 2 points. Looking at the drawing in the bottom right, you see point 1 we call point P, that's x1 and y1. Point Q, that's our second point, we have x2 and y2, and then the vector is the distance between them. The component form of that vector is given by calculating the distances rather than giving the values. Here we have the component form of vector v, where we're taking x2 minus x1 for the first value, and then y2 minus y1 for the second value. Notice that these are not parentheses, and this is not the same notation as parentheses with values. You can calculate component form of a vector if you're given 2 points. For instance, if I said the initial point is 1, 2, and the second point is 4, 5, what's the component form? Initial point 1, 2, terminal point 4, 5, this means that x1 is equal to 1 and y1 equals 2 and x2 equals 4 and y2 equals 5. And so then component form, let's say that this is vector A. Component form of vector A is found by taking 4 minus 1 and 5 minus 2. And then component form would be 3, 3. Now, it's important that your initial point is your x1, y1, and you put it second. In slope, whenever we're calculating slope, it doesn't really matter which point you designate to be point 1 and point 2, because as long as you line things up correctly, the sign will always calculate out correctly. But a vector, remember that there's direction in addition to distance, and so it's important that you're talking about something that is in the correct direction as well. So it's important that your initial point is the thing that you are subtracting from your terminal point. Let's define 2 vectors, v and w, where v is a1, b1, and w is a2, b2. Notice that we are talking about component form rather than ordered pairs of these vectors because we have angle brackets rather than parentheses. Vector v equals vector w if and only if a1 equals a2 and b1 equals b2. This means that their distances from their initial to their terminal for the x component and the y component is the same. So that means that they're in the same direction and they have the same magnitude. We can perform operations on vectors by adding them, subtracting them, multiplying by a scalar. You can do each of those operations. Addition of 2 vectors, you take their a1 plus a2 components and then their b1 plus b2 components. For subtraction, you do a1 minus a2 and b1 minus b2. And then multiplication by a scalar, you multiply the a component by the scalar and the b component by the scalar. Now, that's multiplication by a scalar, not multiplication in general. That's different. With addition and multiplication, we have some properties of vectors that we can use. The commutative properties and associative properties and identity properties are still true for properties of vectors. For instance, vector v plus vector w is the same thing as vector w plus vector v. Vector v plus vector w grouped together plus vector u is the same thing as vector v plus vectors w and u grouped together, added together. Adding 0 to a vector leaves you with the same vector, and adding the opposite to a vector gets you to 0. You've got the distributive property for 5 using a scalar times the sum of two vectors, and C has the sum of two scalars times a vector, and we distribute in both of these cases. And property 7, we have the multiplication of two scalars times a vector is the same thing as the multiplication of a scalar times the vector and then times that other scalar. Multiplying a vector by 1 gets you the same vector, multiplying a vector by 0 gets you 0, and multiplying a scalar by the 0 vector is the 0 vector. So notice that that 0 in property 10 is bold. That is the 0 vector. In property 11, remember that those two lines are telling us the length of the segment. So you're calculating the distance. And so if you take the distance times some scalar, that's going to be equal to the absolute value of the scalar times the distance of the vector. A vector that has a magnitude of 1 unit is called a unit vector. And finding a unit vector in the same direction as a given vector is definitely an important skill to have. Because the magnitude is the length of the vector v, in component form, that is angle brackets with AB. We can use that to calculate the magnitude. The distance between the x coordinates of the initial point and terminal point is the value a, and the distance between the initial point and the terminal point of the y coordinates is the value b. So we can use that to calculate the magnitude by saying that the magnitude is equal to the square root of a squared plus b squared. Because remember that a is equal to x2 minus x1, and b is equal to y2 minus y1. So that is just the distance formula simplified using those values of a and b. To find the unit vector, we take our component form and we multiply it by 1 over the magnitude of v. And we're going to denote the unit vector with a bold U and a little v. If vector v is equal to the component form AB, then the unit vector uv in the direction of the vector v is given by taking 1 over the magnitude of the vector v times the vector v. Well, the vector v is component form AB, so I could say 1 over the magnitude times a component form, which is the same thing as component form A over the magnitude of v, b over the magnitude of v. First, what you would do is calculate what the magnitude is, and then you would use that to multiply by the component. So if you had some component AB, then you're going to calculate the magnitude of that vector by taking the square root of a squared plus b squared, and then you're going to multiply it by AB. So essentially, this is in component form a over the square root of a squared plus b squared, and b over the square root of a squared plus b squared. We have these two vectors that we use that are special. We call them I and j. And vector I is the vector 1, 0, and vector j is the vector 0, 1. They're unit vectors in the directions of the positive x and y axes. And any other vector can be expressed as a linear combination of I and j. Here is a diagram showing the vectors I and j. I is the vector that is on the positive x-axis, and it is a component length 1, 0. J is the vector on the positive y-axis, component form 0, 1. We can represent a vector AB in terms of I and j. We take vector AB and we write it as A times I plus B times J. These are just using as a scalar component, and the values of A and B are called scalar horizontal and vertical components of V respectively. If I had some vector V that was equal to 1, 2, then I could write that in terms of I and J as 1 times I plus 2 times J, which is just I plus 2J. I could then take my vector that's written in terms of I and J and write it in component form by saying, okay, the coefficient of the I is 1 and the coefficient of the J is 2, and go in the other direction as well.